It's a pleasure to be here, particularly in this Ideas Forum, because we are going to be having the opportunity to present a couple ideas here. They're ideas that are very basic and could end up, or very well could end up, into a few products, more than just one product. So I look forward to exposing these ideas here. So in view of time, I'm going to just dive into it. And as everyone knows, we are looking for medical sensing because of the fact that we want to reduce costs, as well as we want to improve our ability to get well much quicker and also be able to understand ourselves better. The low-cost wearable sensing is really what I'm talking about here. And I have a vision of replacing CT scans and MRIs with wearable bands, which are much like your watches right now, that will be able to be put either around your chest or around your head or around your hand here, at different locations, to be able to monitor things about not only about imaging, but also about blood, about conditions, glucose, and particularly multifunctional kind of sensing. So we're going to go from singular sensing, or one sensor, one modality sensing, to multi-modality sensing, as well as imaging, very quickly. Very quickly, I'm just going to jump through all of these slides here, which you can find on yourself. Why are we so much interested in healthcare, and in particular, watching ourselves remotely? Is because the cost really grew dramatically from the mid-2006 to what we are today. We're talking about a huge gap in the income level of our people versus the actual cost of healthcare. And in fact, to put things in perspective, if the products and the food that you buy from the supermarket were to increase at the same rate as your medical costs are increasing now, you would buy a gallon of milk at $48. There's nothing actually that says it more than just that. So how can we reduce healthcare? Well, unnecessary tests in one of them, and unnecessary examinations. So if we can do that in a low cost and still be safe, that's the way to go. We're talking about 27, almost 30% of cost reduction due to unnecessary costs. The way to do that is through wearable devices, ingestibles, and so on. And of course, we can categorize what exists today into the medical devices, which are usually wearable. You attach them to yourself. They're usually single function devices, and you pay also a wireless service to be able to wear them, $50, $40, $30, and so on. They're not integrated. So that's one of the challenges that we're going to face. And then the other class of them is the ingestible ones, or implantable. And there's some very interesting which are coming up, which can go into your retina and therefore do a lot, several things. So these ones particularly coming out from very well-known companies, whether you call it Google, whether you call it Microsoft, or whether you call it, Medtronic, very big companies are coming, also taking images and transmitting them from ingestible pills. That's also happening, as well. And there's a number of them which are in research, where the goal is to do multifunctional, detection of different modalities, whether it's glucose, whether it's about your heart, whether it's about your, how well you perform, to the different drugs that you're taking during the different periods of time, and so on. And Dr. Gabby mentioned some of that, which is really that continuous monitoring, even while you're sleeping, being very important. So what are we offering here? We have a technology. It's a textile technology, very well actually documented. In fact, a couple of years ago, we've been in New York Times about this when we first introduced it. And the main idea is that you wear the sensor just like you wear your shirts today. That is, you will not have you will not feel anything different. But it will be a sensor. And one of the things that I thought about is utilizing the surface area. It's a big surface area. And I know very well from imaging that I need a big area to be able to do very well detailed image of the body. So if I have a big area, I'm going to be able to do good detailed images. So I'm actually using that knowledge to wear a bigger piece around me. So it is very important that this is not visible to me. And it's also not bothersome, right? So therefore, there's compliance issue. Another thing, let us make no mistake about it, you're going to be untethered. That is, your cell phone will connect to your clothes one of these days, and you will be able to therefore talk a lot much easier, transmit high-speed data, and things like that. And therefore, you will not be relying on where you put your cell phone and therefore short it out and have unreliable communications, particularly for downloading movies or other high data stuff. So we tested it, and our fiber technology is almost, although it looks like a regular cloth, it's pretty much in conductivity, maybe not as good as copper, but it's very close to it, actually, very close to it. Very small, minute differences, about 0.1 dB. You know, for those of you who understand dB, it's a very small number. And also, we went ahead, and because we wanted to test this, so we went ahead and made up a number of experiments. So here is the patch, here's the textile right into your shirt. And also, we created a Bluetooth communication device so that you can walk around and collect data for yourself. This is not a commercial version, but something that we can do the job. Also, we've introduced a harvester because no batteries. This is very important that we don't replace batteries. And as you will see later on, we will also have a neurosensing device, and you're not allowed to put anything into your, close to your brain that generates any heat whatsoever. So we need to harvest things from the ambient. So we introduced devices that can harvest things, and we've demonstrated some very interesting experiments that Hewlett-Packard was looking for the other day, and they called us and says, we've looked around about harvesting the ambient RF energy, and you guys seem to be the only ones that you've been able to demonstrate it, and we feel confident that you have something real. Stanford did it, others did it, but you guys have something real. So we're very pleased, and we're working with them right now. So let's talk about these two devices, which are much closer to reality. So as I said, we are going to exploit the area, right, of our body, which is very big, and the fact that it's going to be inconspicuous. So we're going to make a metallic version of that, but it's going to be textile at the end. You're going to see in a couple slides, it's going to be textile. And we're going to put it on the body, and we're going to play some tricks to see how we're going to be able to see the details of the mass and identify the dielectric constants very deeply inside it. So the first experiments were done to see how big should we make this sensor over here. And you can see that as we put 4 probes over here, probes is these strips over here, 1, 2, 3, 4, 5. So 4, you can't see anything. But as you go all the way to 16 or 14, you can see a huge difference now in between one dielectric versus another, or as you are inhaling, you can see a big difference between the lungs having full of air or the lungs not having air. So that's a voila. I can really see now and identify whether you have water in your lungs or something else is happening. There was another problem with it. This is a very difficult problem mathematically. I know that it's called inverse scattering, and it's very well known in imaging underground Earth or in imaging, different, through the walls and so on. Very well known problem, and we need to solve huge integrals and integral equations, which is a very computationally intensive method. So I said, let's, instead of solving these huge integrals, let's propose the solution. If the solution is bad, it'll never give you any answer, which is worth anything. But if it's good, then all I got to do is fit the coefficients. So I proposed a solution for the coefficients, for the dielectric constant at different locations, here. And I proposed that we determine these coefficients. It's a linear representation. Maybe it's not going to be so linear. Maybe it's quadratic, cubic. But this is a game-changing approach of solving a problem rather than trying to find out what is epsilon. I said, let me give you an expression, and then you fit it. You do curve fitting method. Very nice approach, and let's see how it works. So we've done we put the sensor in front of various bodies. Here's the sensor over here, and here's the various dielectric bodies. And you can see the error is about 4%, 6%. These are very good errors, given the uncertainties involved. And also, we did real experiments with partners at Mississippi State, and here is the lung over here, fresh lungs from a pig, and we've compared it very well between measurements and our analysis. And here's the textile version. So it does exist, although I'm interested at this moment in perfecting this representation. So I'll leave this project, which is ongoing. And let's talk about a National Science Foundation project here, which we recently were lucky to win a $2 million award on this process, on this project. And the main idea is that we want to read the neuron signals, the neurosignals from your brain while, for example, you have epilepsy or you have other issues, and therefore be able to see how can we correct or take a pill at that particular time, or do other things that will allow you to either sit down, for example, at least give you some warning of malfunctions within the brain. What's the problem? The signals in the brain are extremely, extremely small, microvolts, for example, and you will see that in a moment. But in the end, our goal is to put a small band around, or maybe your hat that you're wearing, and nobody will ever detect anything that you're even wearing or there's anything to do with it. So let's see what the challenge is. So the first circuit was done by our collaborator at Arizona State, and it didn't, at least it identified the problem, but it didn't work. We were not able to detect much of signals. And I'll explain that in a moment, but this is what we're talking about, putting the sensor right above the dura, which is really what protects your brain pretty much. The cranium is not an issue whatsoever. That's not, the skull is not an issue whatsoever. The signals here are unfortunately as low as 10 to 100 microvolts. Microvolts 10 to the minus 6. They're very, very small. And usually our communication devices work with this kind of level of voltages. However, we encode them. And in this particular case, we can't encode this. We're going to get what we get. So we typically have GSM, for example, CDMA, and things like that, or PCS, UMTS. These are the coding schemes that we use to be able to detect these signals at very low levels. And we did an analysis to see what are the problems that we're dealing with. Well, I have to be able to detect a signal of minus 130 dB below a milliwatt. That's 10 to the minus 13. That's the signal level. It's very low. It's actually at the level of the GPS signals, which is heavily encoded. And so that also we know that based on the fact that we have minus 80 dBm, minus 80 dB here right at the sensor. So this means I got to have a circuitry here that has losses of less than minus 50 dB. And these are the rules of the game. And you will see that it's done. Actually, we did it about 3 weeks ago. We've demonstrated about 3 weeks ago in the lab. It's a big demonstration. I think it's an event which is something to write about. Another thing is we need to detect all these signals across the entire bandwidth, right? So your neurosignals have bandwidth from about 100 hertz all the way to 1 kilohertz. And in order to get the signal correctly, you need to detect it across the entire bandwidth. And these are the levels. And you can see that at the low frequencies, the levels are kind of high, but at the 1 kilohertz is very low. So we begin to see that, and this one is, we can afford like 60 dB at 100 hertz, but at 1 kilohertz, it's got to be, we can afford only 50 dB loss. So it's challenging, but things are good. So what do? Well, we ended up a little interesting, smart approach, I would say, with some of the students. The students went and they put this, what we call anti-parallel diodes. And one of them allows for the negative, the other one allows for the positive. So you get another 3, 4 dB. They've also been able to separate the signals from the DC signals from the AC signals, so they're able to create a lot of isolation, and this means low noise levels and things of that nature. We've also been able to work with the second harmonic, not the first harmonic, so it's a little cleaner, harmonic. There was some math we went through that, and we went ahead with our first experiment. So unfortunately, this represents your brain over here, which is the implant is over here. The interrogator, by the way, there's no battery, of course, in the brain. So there's no, the interrogator has all the battery, and it works like an RFID. So you have an RFID inside the brain, basically. So it just has a little capacitor that you see over here, this little capacitor, and it's going to charge up because a signal will be charging it. And after it charges up, then it will power up the diodes, and then they will send out whatever signals they have collected from the brain. So so it all worked out, and we were able to compare our analysis, and we're able to detect it very well. You'll see that in a moment. So here's the detected signal. Quite impressive, quite clear. We transmitted it. We got back what it was in storage, and we've been able to achieve our minus 50 dm detectable signal across the entire band. This was done already before at Arizona State. We were able now to go all the way through the entire bandwidth. So it's a very monumental development. I think we're standing at being able to begin to see how we're going to assess what we call consciousness. That is, as we walk around, as we feel things around, how do we react? What do our neurons are doing? And I think it's an exciting moment to create some realistic study of ourselves while we're doing some normal things. Thanks very much.